Sorry, I was muted. Hi.
This meeting is. Oh my gosh, this is so weird. I got this weird, this lady talking to me. This meeting is being recorded. I've never had that before, so hopefully everything.
Oh, we hear it on our end every single time.
You do?
Yeah.
Wow. I've never heard it before. Hopefully I'm going to be able to share my screen. Okay, so hi, let's get started here. We're looking at confidence intervals. I have two documents that are uploaded in the Zoom meeting area. One is on proportions, confidence intervals for proportions, and the other one is confidence intervals for the mean. These are separated problems, but today, actually, when you're looking at 9.3, I think it's today. Yes, today. So today in 9.3, it should give you a variety of problems because it's a section of which procedure do I use. And then you have to decide whether you're doing a confidence interval, you're creating a confidence interval on a proportion, or if you're creating a confidence interval on a mean. So we're going to start with that. Let me look at here and then here. Okay, so it didn't work. Oh, I didn't do it yet. Okay, hang on. Oh my goodness. Oh, is it Friday yet? It's only Tuesday. Oh, now it says connect. This is so weird. I've never had this before. Trust it. Come on. Oh, I unconnected it. Oh my gosh. Okay, here we go. Yes, success. All right, so after I fumbled with my iPad, here we are. So this is what we did last time, right? I gave you kind of a flow chart maybe of sampling distribution. If we're looking at sample mean, these are the symbols we use. These are the characteristics we need to check. If we're looking at proportion, these are the characteristics that we need to check in order to use a normal model, and then what a normal model consisted of. So same thing here, confidence interval. Confidence interval, if you're looking at a proportion, confidence intervals estimate the population. So you're always building your confidence interval off of the statistic. So whatever your statistic is, if it's proportion, it's going to be the sample proportion. If it's mean, it's going to be sample mean. So you're building your confidence interval off of the statistic. And then you're adding and subtracting some error, and you get this lower bound and this upper bound. And you're confident that the population is going to fall between those values. That's what you're creating. So for proportion, you take p hat and you add and subtract this error, where your error is your critical value, your z critical value of alpha over 2 times the square root of p hat times 1 minus p hat over n. We add and subtract that error and we get the lower bound and the upper bound, and we're estimating the population proportion P. So when we were doing compound inequalities, we were looking at things like this, where we would have the parameter in the middle, so the population parameter P, and then we would have numbers on each side. So this is what you're creating with proportion. We know it's connected to a critical value. And for proportion, it's always Z. For mean, it's going to be T, but for proportion, it's Z. And your critical value Z is based off of your level of confidence. I'm going to talk all about this specifically with each problem, but your level of confidence dictates your alpha level. So if you have a 90% level of confidence, alpha is 10%. So then you're looking at Z alpha over 2. So you're looking at Z sub 5%, Z sub 0.05. We will continue with that idea later. Okay, let's compare that now with the mean. So with the mean, You're estimating the population parameter mu, where you're still taking that sample statistic, you're taking X bar, and you're adding and subtracting the error. Well, your error is a little bit different. Your error in this case is a critical value with T, the student's T distribution. And then we multiply that times S over square root of N. Your critical value T is dependent upon the level of confidence and the degrees of freedom. Your degrees of freedom are N minus 1. So when you're building your confidence interval, you're estimating the population based off of the sample. You get the lower bound and the upper bound, and you feel confident that the true population parameter lies between those values. So as I mentioned, your critical values for proportion, you have a Z critical value, which you use the normal. And for your critical value for mean, we use T sub alpha over 2, which is your T distribution. Okay. A couple more things and then we'll get into the problems. When you're estimating a population and the requirement check fails, such as you do not know if the population, I'm talking about mean. So with mean, the requirements are, does the population does the sample come from a normal distribution? Is the population a normal distribution? If you do not know that, you check the sample size. If the sample size is small, then you have to go through what we did in 7.3 and you have to assess the normality. So if the population is not normally distributed and the sample size is small. So if the sample size is more than 30, we're fine and we can use our the T distribution, those tools. If your sample size is small, then we have to check normality. You do a QQ plot with StatCrunch, you look at the linear pattern, you calculate your correlation coefficient R, and you compare what you calculated to the critical value from the table or I don't have it right now, but it's the critical value for the normality, the normal probability critical value table. You also need to draw a box plot and do an outlier check. So this is all assessing normality. Assessing normality, you do the QQ plot. So that was from 7.3. You look at the linear pattern, you calculate R, you compare R to the critical value. If your calculated R is greater than the critical value, then you are comfortable assuming normality. The box plot, you do outlier check. So you take your first quartile and you subtract 1.5 times the IQR. You're checking your lower fence and your upper fence values to see if there's any values that fall outside of the lower fence and the upper fence. Those would be considered outliers. Okay, let's see, I think that was it. Okay, so those are just like notes and not a formula, a recipe, maybe a recipe of what to check and what to look for. When you're looking at confidence intervals, you're looking at maybe a 90% confidence interval, and then you have these tail ends. So then your alpha would be 10%. So your Z sub alpha over 2 would be 5.05 over here. That's your critical value. And the 0.05 comes from you're splitting the 10% into two tails. So 5% in the right tail, 5% in the left tail. But that's where your critical value comes from, whether you're using Z or T. So I wrote Z, but T would be the same. So your error is dependent upon, so E in our formula when we were looking at E. So your error, it depends on the level of confidence, because that's going to dictate what your alpha is, which when you split that in half, you get your critical value. So it depends on your level of confidence. Okay, let's move into those problems now. We're going to let's look at proportions first. So luxury or necessity. I gotta find it now. Okay, so this is the one I'm looking at. So confidence interval for proportion, luxury, or necessity. Random sample of 1003. Okay, so there's a random sample. This is my N already. I don't need to write all that. This is your N. Let's say a random sample of 1003 adult Americans was asked, do you pretty much think televisions are a necessity or a luxury you could do without? Of the 1003 adults surveyed, 521 indicated that televisions are a luxury that they could do without. So the 521 is your X value. You're counting how many. Obtain a point estimate for the population proportion of adult Americans who believe televisions are a luxury they could do without. So part A, your point estimate is just your sample proportion. It's just one value. And that's where we've grown from just having one specific value that estimates the population to now confidence intervals, which is an interval of values that estimate. So for p hat, we would get 521. We would divide it by 1003, and we would get 0.519. This approximately. Okay, so approximately, I'm just going to round it to 3 decimal places for the purposes of this assignment. Okay, so we have my point estimate. And then it says part B, verify the requirements for constructing a confidence interval about P are satisfied. So if we're going to verify the requirements, we know that N times P hat times 1 minus P hat has to be greater than or equal to 10. This is in order to use the normal model. Okay, so we have 1003 times 0.519 times 1 minus 0.519. Is that greater than or equal to 10? When you multiply this out, you get 250.39, and that certainly is greater than or equal to 10. So that first requirements checks. And then you also want to ask, is my sample size smaller than 5% of the population size? So is 1003 less than or equal to 5,000, not 5,000, 5% of the population, and we're looking at adult Americans. So yes, certainly 1003 would be less than 5% of all adult Americans. So both of those check. So those requirements check. Part C says construct and interpret a 95% confidence interval. Okay, so we're looking at a 95% confidence interval for the population proportion, for P, population proportion, we know what we're looking for, of adult Americans who believe that televisions are a luxury they could do without. So in order to construct that, it met the characteristics of a normal model. So now we know that we're looking at P hat plus or minus the error. So I already have my P hats 0.519 plus or minus this error. Well, this error is calculated by taking the critical value Z sub alpha over 2 times the square root of P hat times 1 minus P hat all over N. So I can calculate what's under the square root because I have my p hat value, 0.519, but I need to find z alpha over 2. So in order for me to find my critical value, I'm going to draw my diagram. This is going to help you extremely in the chapter 10. So really hone in on critical values and what they're related to on the graph. So my critical value, if it's 95% here, then that means my tail ends, I would have 5% on each tail. So this would be Z sub 0.025 because I have 2.5% on each tail. So in order to find that, we can use inverse norm. You can go to StatCrunch. We've been doing this a lot since chapter 7 even, where we're trying to find a value given a probability or an area. So in StatCrunch, you would go into normal because we're using a normal calculator and Z is what we're looking at. So you would go into stat, calculator, normal. You would put in mean of 0 because we're looking at a Z-score, standard deviation of 1, and then you would put in greater than. So X would be greater than, and I know StatCrunch will say X even though we're finding Z. It's just, that's the way StatCrunch is, and we know we interpret it as Z. So it'll say probability of X, you choose a greater than sign, you leave whatever number that is blank. So probability X greater than, leave that number blank because that's what we're trying to find, equals 0.025. So you leave that part blank because that's the number we're trying to find. So the critical value then would pop up to be 1.96. So right there on the number line, 1.96 is the critical value that separates that top 2.5%. Okay, so that in my error formula then, my error would be 1.96 critical value times the square root of 0.591 times 1 minus 0.591 all over 1003. Okay, we get an error to be approximately 0.031. When you calculate that. So I remember that this is what I'm trying to find. My goal, there's my goal. Goal is find that confidence interval. So we have 0.591 plus or minus. Now we have this error of 0.031. So the lower bound would be 0.591 minus 0.031. So I'm estimating P. So I put P in the middle. My inequalities show that P is between 0.591 plus 0.031. So 0.488 less than P less than 0.55. So we are 95% confident that the population proportion of adults or adult Americans who think TV is a luxury they can do without is between 0.488 and 0.55. That's interpreting your confidence interval. So you're 95% confident that the population proportion of adult Americans who think TV is a luxury they can do without is between 0.488 and 0.55. Yes, when you go into StatCrunch, you can pop into these, boom, boom, right away, pretty quickly. But if you're not understanding where those numbers come from, this means nothing. So I'm going through this all the way through it. One, to help you with critical values and get you to understand critical values are related to the level of confidence, how important that is. I'm also setting you up for success for chapter 10 when we're doing all this detail. But you're taking your statistic, your p hat, your sample statistic, your point estimate. I'm using all the words that you've been taught. So your point estimate, your sample statistic, your p hat, your sample proportion, and you're adding and subtracting this error. So this error is dependent upon z alpha over 2 square root of p hat 1 minus p hat over n. It's dependent upon the sample size. It's depending on your level of confidence. And then you add and subtract this error to your statistic, and then you get these lower bound and upper bounds that you feel confident that the population proportion falls between. Okay, so let's keep going. I'm not really going to bring you into StatCrunch unless there's a question about that, but I think it's really basic. If you have to go to stat, I think, and then you go to proportion stats. That's how you go, and then you would pick you have to click on confidence interval. So that was one of the issues. If you have a question about StatCrunch, you let me know. All right, let's go to number 2 now. Number 2 says, a Rasmussen report national surveys of 1,000 adult Americans found that 18% drink smoothies as their only source of consuming greens. The margin of error for the survey was 4.5 percentage points with 95% confidence. Explain what this means. So let's dissect a few things. I'll just do it up here. I'm going to write above that paragraph just because that's where I have the space. So we know that N is 1,000. Sample size is 1,000. We know that P hat is 18%. So like we did before up here, we had to actually calculate our point estimate. We had to calculate our point estimate given number of successes over the sample size. This problem, we're not counting it because we're just given this percent. That still is our sample because a survey of 1,000 adult Americans found that 18%. So 0.18. We also know that E, the margin of error, is 4.5%, or the margin of error is 0.045. So my confidence interval, P hat, plus or minus the error, is 0.18, plus or minus this error 0.045. So 0.18 minus 0.045. I'm estimating my population proportion P. So 0.18 plus 0.045 will give me the upper bound. So 0.135 is the lower bound, and 0.225 is the upper bound. So we didn't have to calculate error. It was already given. The margin error was already given to us. But we calculate our confidence interval based off of the margin of error and the point estimate. So then we can say I am 95% confident. And it was 95%, right? Yes. Okay, with a 95% confidence. So that's where I'm getting my 95%. I'm 95% confident that the population proportion of adult Americans who drink a smoothie as their only source of greens. Is between, and since we were given a percent, we could answer in a percent. So I could say between 13.5% and 22.5%. But I probably would, if I gave it in percents here, I probably wouldn't use proportion. I would probably up here instead just write the percentage. Whoops, wrong pen. So instead of proportion here, I might just write percentage. And right. If I'm going to give it in that format. Okay, let's move on now to part 3. Part 3 says, I don't know if you all do this, but I think this is really gross. Don't bring your phone into the bathroom or your iPad or whatever. Bring something that you can throw away. In a survey conducted by the marketing agency 11 Mark, 241 of 1,000, so 241 of 1,000 adults 19 years or older stated that they bring and use their cell phone every trip to the bathroom, texting and answering phone calls. Part A, what is the sample in this study? What is the population of interest? So sample, part A, the sample is 1,000 adults, 19 years or older. And the population is all adult Americans. Oh, not adult Americans. This is all adults 19 years or older. Okay, so the sample is just the 1,000 adults, but the population is all of the adults in that specific age group. Okay, part B. What is the variable of interest in the study? Is it qualitative or quantitative? So what is the variable of interest? What are they actually measuring?
Qualitative, because it's a yes or a no.
Yes, correct.
Right. Whether they, okay.
Yeah, so the variable is going to be whether they bring the phone in the bathroom or not. Whether they bring the phone in the bathroom to talk and text. So we all know what that, we all understand the problem without me taking time to write it down. So whether to bring the phone in the bathroom, this is qualitative, because yes, it is either they're bringing the phone in or they're not. Nice work. Part C now. Based on the results of the survey, obtain a point estimate for the proportion of adults 19 years of age or older who bring their cell phone into the bathroom every trip. So P hat, because we're measuring proportion, X over N, and this, they said 241, I believe, yes. Okay, so 241 out of 1,000, so 241 out of 1,000, or we can write that as 0.241 in decimal. Part D, explain why the point estimate found in part C is a statistic. Okay, it's a statistic because you're taking it out of a sample. You're doing a calculation off of a sample. Out of the 1,000 adults, 241 bring the phone into the bathroom. So that's why it's a statistic. It's not out of the population, it's out of the sample. And the other question says, explain why it is a random variable. Just because it may change on different samples. So if I on a different time I took another 1,000, I might get 219, or I might get 276. So because the sample size, you're randomly choosing a sample size, the point estimate is going to vary. It may change, it just may change on the individuals that are selected. And what is the source of variability in the random variable? The main source is just the people that are selected. So the individuals that are selected, that's going to make the answer vary whether they bring the phone in the bathroom or not. Okay. Part E. So you take your own notes on that. I'm not going to take the time to write it down just because this is way too short of a class. All right, construct and interpret a 98% confidence interval. So we have a 98% confidence interval. And then I right away immediately say, what am I making a confidence interval on? Is it a mean or proportion? And it says construct and interpret a 98% confidence interval for the population proportion. So I know I'm saying for P. Okay, so because I'm looking at a confidence interval for proportion, my goal is to find P hat plus or minus the error. P hat, we already found above in part C, so 0.241 plus or minus this error. So now I need to construct the error. The error is my critical value, Z sub alpha over 2 times the square root of P hat times 1 minus P hat over N. So I need to find Z. I draw my normal, my standard normal curve. I know this is 98%, which means my Z sub alpha over 2. So I know that there's alpha is 2%. Alpha is 2% since my confidence level is 98%. So alpha over 2 would be 1% that is in each tail. So then you would go into StatCrunch, or you would go do your inverse norm on your calculator. So StatCrunch, we know this area is 0.01, but we don't know the value. We have the mean of 0, standard deviation equals 1 because this is a Z-score, and the probability of X, we use a greater than. I leave blank the number I'm trying to find because that's the number on this number line that separates the top 1%. Okay, when we do that, we get this value of 2.326. So we get 2.326. So in my error formula, I get 2.326, and then I'm going to multiply that times. I got to get myself a little more room. I'll go ahead and write down here another page. Okay, so in my error formula then, error equals my critical value, 2.326 times the square root. P hat was 0.241 times 1 minus 0.241 all over the sample size. Our sample size was 1,000. And we get an approximate value for error to be 0.031. Isn't that what we got last time? Okay, the error doesn't always come out to be 0.031, just by chance, all right? Okay, so P hat then, plus or minus the error. My P hat was calculated to be 0.241, plus or minus this error we calculated 0.031. So 0.241 subtract the error, 0.031. P is between that lower bound and the upper bound, 0.0241 plus 0.031. And we get 0.21, P 0.272. We are 98% confident that the population proportion of adults 19 years and older use their phone in the bathroom to talk or text or surf, whatever else you do in there. 0.0241, let's see, is between 0.21 and 0.272. So I said I wasn't going to go through the StatCrunch. On the calculator, I will just mention in case you wanted to know, because your calculator is really convenient to use as well. So on the calculator, you would go to Stat, press your Stat button, and then you arrow over to Tests. So on the calculator, if you press Stat, and you arrow to the right over to Tests, and then on that menu, you would choose 1, which is number 5. Let's see, it's interval. I've got to find it. You have to arrow down. Looks like it is. Oh, there it is. On the test, we want interval. Okay, so you arrow all the way down until you see A. So when you arrow down to A, then it will say A will have 1 dash prop, so proportional Z interval. So if you select that, so arrow all the way down to A, and then you'll see 1 dash proportion Z interval. Your X value is 241. Your N value is 1000. Your confidence level 0.98. And then you calculate, and it will give you an interval notation. At the top of your screen, after you hit enter, you enter all that in, this is what you get. So that, compared to what we did by hand, is still, if you round, it's still pretty similar. So another way to use your calculator quickly to get to the confidence interval, the lower bound and the upper bound. But don't just jump into this and punch in numbers if you're not understanding what you're finding. Okay, let's move on. We have a lot to talk about. Part F, just let me mention this to answer part F. One ensures that the results of the study are representative of all adults 19 years of age or older who bring their cell phone every trip to the bathroom. So random sampling is what's required. So that's how we can ensure that it represents what the population is because how you sample it. So back when we learned sampling methods, way back in the first chapter, maybe even in the first week, and we talked about systematic sampling and stratified sampling and cluster sampling and random sampling, all of those methods, that was to ensure that we were representing what the population is. That's what our goal is. We take a sample, we look at the characteristics, we analyze that, and we infer what the population is doing. So the random sampling is what's required to ensure that the study represents the population. Okay, let's move on now to the second worksheet. The second worksheet is on confidence intervals for population mean. Okay, so I'm really old, so some of you may not remember this, but I totally remember these commercials. A Tootsie Pop, so that's that candy, and it has like the chocolate, like a lollipop, and it has candy on the outside, like hard candy on the outside, then inside like this chewy chocolate center. That's what a Tootsie Pop is. A Tootsie Pop is a sucker with a candy center. A famous commercial for the Tootsie Pops once asked, how many licks to the center of the Tootsie Pop? in an attempt to answer this question, a college student asked 19 volunteers to count the number of licks required before reaching the chocolate center. The mean number of licks required was 356.1 with a standard deviation of 185.7. Find and interpret a 95% confidence interval for the number of licks required to reach the candy center of the Tootsie Pop. Okay, so we read the whole problem. We have a sense of what's going on here. So backing up a little bit, we need to, it says confidence interval for the mean. So we're already cued in on what we're finding, but take a step back before you start with any calculations, before your head starts going where I need to go and stack crunch and what I need to do is what are you finding confidence interval on? It says find and interpret a 95% confidence interval for the number of licks. That's a count. That's a discrete count. So we know that if we're counting, we're probably going to be looking at a mean. It's not a proportion. It's not the proportion of or the percentage of. It's saying how many. So we know that we're doing a confidence interval on the mean. Therefore, we're going to look at X bar plus or minus the error. And in order for us to, okay, let's just keep going. So X bar, are we given X bar? We're given that the mean, yes, the mean number of licks required, we have that. So we have X bar as 356.1. So my error is going to be for mean, I know it's T alpha over 2 times S over square root of N. Okay, so my critical value is T. Right now, what I have, I'm going to have to find my critical value, but I do have S because it says standard deviation up here. Standard deviation is 185.7. And I know there were 92 in my sample, so square root 92. So my task is to find the critical value. So before I jump in and find the critical value, can I assume normality? I have to check that always. Can I assume normality? It doesn't say that the population or the sample comes from a population that's normally distributed. It does not say that the sample comes from a population that's normally distributed. But we do have a sample size of 92. So since N is 92, which is greater than 30, then we can assume normality. Therefore, we can talk about the T distribution and the critical value T. So I'm going to do exactly what we did with proportion, and that was to draw your T distribution curve. T distributions still have 0 in the middle, but remember that the T distribution changes with the sample size. So we have degrees of freedom that are associated with the T distribution. N is 92, so degrees of freedom would be 91. Your degrees of freedom affect the shape of the T distribution because the T distribution changes with the sample size. It can have a higher peak, it can have more of a flat peak. It still has the bell-shaped curve, but it changes with the degrees of freedom changes with the sample size, the curve does. So I need to look at a 90, what was the number? 95%, right? 95%. So 95% confidence interval, which means alpha is 5%. So I'm looking at Z sub 0.025 because I'm looking at the critical value that separates that top 2.5%. when I go to my calculator, I do not use normal, and it's not Z. I just made a big mistake. I'm going to highlight that big. That's a big mistake right there. Okay. It's not Z, it's a T. If I wrote Z, then I would go to my stat calculator normal. I'm not looking at a Z. I need a T distribution. So I need to make sure that this is a T, not a Z. So then you go stat, calculator, T statistics, I think. I have it in front of me right now. That sound
It
right?
might just be the capital T, the uppercase T. I think that's what that one is. I do believe.
I should have looked at it right before and I forgot. If we have time, we'll jump into it. But
I'm almost positive it's just T.
Okay, people, you should know how to do that. If you don't know how to do that, ask me, okay? Similar process, but make sure you're choosing the correct calculator, the correct inverse, the correct process to find it. Did you find it?
It is just capital T. Yeah, I just found it in my
Okay,
notes.
so
Yeah.
it's stat calculator and then capital T.
Mm-hmm.
Thank you. Thank you so much. All right, so then we get the critical value here. And it'll ask you for the mean. I think it's not going to ask, it'll ask you for the mean and the standard deviation. So the standard deviation is 185.7. And then it will also ask you for degrees of freedom, I believe. And your degrees of freedom will be 91. And then you'll have the probability and you'll have X, even though we know it's T, we'll say greater than. We know the area is 0.025 and we leave this spot blank. And if you use your calculator, just on a side note for your calculator, on your calculator is inverse T, which is, so if you go second bars, and this is number 4. Number 4 is inverse T. So make sure you're using inverse T and not inverse norm. The other one on your calculator is inverse norm. Inverse norm would be if you're finding a Z critical value, but if you're finding T, you would use inverse T. Side note there. All right, so the critical value.
I do have a quick question. For the mean, we do have the mean for that problem. So why would I don't think the T calculator
It's not asking you
for the mean and standard deviation. I believe it's just the degrees of freedom. I believe.
I think you're right. I think it is just degrees of freedom. What's wrong, Pen?
Because if we have the mean, wouldn't we input the mean if we're inputting the standard deviation?
Yes.
Okay.
Yeah, and we're looking at the mean of, so the issue here, the mean for the T, I keep erasing things. Quit erasing stuff. Okay, hang on. So the mean for a T distribution is 0.
Right.
But the standard deviation changes with the sample size. So what I did write down was correct for distribution because the standard deviation changes with the sample size. But it does, I think you are exactly right. It does only ask for degrees of freedom.
Okay. I just want to make sure I'm inputting them right.
Yeah, it only asks for degrees of freedom because that the degrees of freedom affects the shape of the distribution because the sample size affects it.
Okay. Perfect.
Yes, thank you for asking about that. Okay, so the critical value that we find either by technology or by your calculator, we end up getting 1.986. So just be aware, 1.986, and that makes sense on your graph. That makes sense. That looks like it would be approximately 1.986. If you got like 19 something or you got negative, you probably did something wrong. And if you're off by just a few decimal places, excuse me, it might be because you're not using T and you're using the normal. So that could be a case where if you're getting an incorrect critical value, it might be because you're not using the correct operation for T versus normal. Okay, so now I've been talking so much today. Here we go. I have my 95%, oh, my pen, 95% confidence interval for mu. So X bar plus or minus the error. The sample mean was given to be 356.1 plus or minus. We have to calculate the error. So my error was running out of a lot of room. So I'll do the error over here. So my error is my critical value T alpha over 2 times S over the square root of N. So my critical value we found to be 1.986. Standard deviation was given to be 185.7. And N is the square root of 92. So make sure here that you're putting in N and not the degrees of freedom there. Sometimes that can get confusing, but square root of N, not the degrees of freedom there. So then your error would be approximately 38.45. So that's what I add and subtract to get the lower and the upper bounds. So 356.1 minus 38.45. And I'm estimating the mean. So the mean is between 356.1 plus 38.45. So 317.65. The mean is between that lower bound and the upper bound of 394.55. And then you could write your sentence. I'm just going to speak it just to save time because we're really crunched on time. I am 95% confident that the population mean number of licks required to get to the chocolate center is 317.65, is between 317.65 and 394.55. Right. This last problem now. This last problem is giving us data and not a summary. So before we have been given just the sample mean, but now we're actually given data. So this is, following data represents the repair cost for a low income collision in a simple random sample of mini and micro vehicles. Okay, so we have 10 values here. How can we verify that it is reasonable to conclude the data come from a population that's normally distributed? So right now my sample size is 10. Yeah, my sample size is 10. And that's less than 30. So I can't assume it off the sample size. And already it doesn't say anything about population being normally distributed. So that's already off the table. The next thing you would do would be to check the sample size. It fails there. So that's where I said you have to go and make your QQ plot. So in order to verify, so this is where you would assess your normality. And if you need to refer back to 7.3, that's where you would find all those tools. I'm just going to speak through them since we don't have time to jump into StatCrunch to do it. So you would enter those 10 data values in a list in StatCrunch. Enter all those data values in there. You would create, the first thing you would do is you would enter your data into StatCrunch. And then you would create a QQ plot, because you're looking for, it's the normal probability plot. And you would calculate R. Okay, so R, when you calculate R, you get 0.958. So without taking you into StatCrunch and taking the time to do that, when you create your QQ plot, I think there is a button that you click that says to include the correlation.
There is, yeah.
Yeah. So make sure you check that so you can calculate the correlation of your data values. And then you want to compare that to your critical value. Your critical value, I think I put a table in Did I give you a table in the Zoom? Thank you, Crystal. So in the, the table, I just looked at this before. I'm sorry.
Now, would it be, is it for, yes, okay, got it. For the probability plots?
Yeah, so on the table that I gave you, does it have two tables or just one table?
It has two. I have one for a normal probability plot or the correlation coefficient.
Yes. So choose the one for the normal probability plot.
Okay, so for a sample size of 10, it's 0.918.
Yes. Okay, so that goes from your critical value. When you compare it, you're looking at the absolute value of your calculated R to make sure that it's greater than the critical value. So 0.958 is greater than 0.918. So we would assume normality there. You would also, that's just one way to check it. The second way, so there's part A. I did it by one. So one would be entering your data and doing your QQ plot and making sure that you have your correlation, your calculated correlation is more than the critical value. The second thing is the box plot. So on your box plot, you want to calculate the lower fence and the upper fence. So the lower fence would be your first quartile minus 1.5 times the interquartile range. And the third quartile plus 1.5 times the interquartile range is your upper fence. And the interquartile range, remember, is the distance between the third and the first quartile. So just that subtraction. Okay, so when you do that, I can type those in here real quick. So the first quartile is 773, and you subtract 1.5 times the interquartile range is 1864. So we get a value of negative 2023. If you take the third quartile, which is 2637, and add that to 1.5 times the interquartile range, which is 1864, we get a value of 5433. Okay, so then you're checking to see, do all your data values fall between? All data is between the fences, so no outliers. Okay, so that's what you need to do to check normality. The QQ plot, and then also check for outliers. So we're good to go. Now we can move ahead. And by moving ahead, that means we need to go back and remember what the problem is. So here's the problem. How can we verify? We just did through all that. We just checked for outliers. So part C, construct and interpret a 99% confidence interval for the population mean cost of repair. I am not given a mean. So because I have all of this in StatCrunch, I need to find the mean and the standard deviation. Remember that your standard deviation is not adjusted. So let's see. The standard deviation for S is just regular standard deviation. If you're looking for population standard deviation, that's when you would choose unadjusted. So this in StatCrunch, S is just standard deviation. So you find the mean and you find the standard deviation. And those end up being, the mean is 1756. So the mean that you find in standard deviation calculated to be 1756.50. So these are in dollars, $1,756.50. And then the standard deviation is 1007.45. It's a very large standard deviation, isn't it? But if you look at the values, the smallest value is 743. And it looks like the largest value is up here at 3,000. So quite a big difference. So that's why the spread is so, oh, here's the bigger one. That one's bigger. Quite a difference in spread because that's why the standard deviation is big. Okay, so now we need those to look at my 90, again, 90 what? 99%. Okay, 99% confidence interval for mu. X bar plus or minus the error. X bar is $1,756.50 plus or minus, and we need to calculate this error. The error is critical value T sub alpha over 2 times S over the square root of n. So I need to find the critical value. 99% confidence interval. So alpha is 1%. So Z sub 0.005, because it's only 0.5% in the top tail. I'm going to look for that value. Either going to StatCrunch. We got to use degrees. Oh, I did it again, didn't I? Look what I did.
I was going to tell you. I was giggling, sorry.
Good. Again. So that is not right. We need T, okay? So you're looking at a T distribution. So you're going to go into your StatCrunch and find calculator T, or you're going to use inverse T on your calculator in your TI-84. So we end up getting critical value of 3.2498. And remember, degrees of freedom, we'll have to use that. So degrees of freedom are 9 in this case. Okay. All right. So now I have enough information to calculate the error. So my error is going to be T, which is 3.2498 times S, which is 1007.45 divided by the square root of 10. So the error comes out to be 1035.33. And when I go back to X bar plus or minus my error, my X bar is 1756.50 plus or minus the error of 1035.33. Okay, so that error is here. We get the lower bound by subtracting. We're estimating the population mean, and then the upper fence, but this is not a fence, this is a bound. Fences are when we look at outliers, when we're looking at upper and lower fence in the box plot in that visual for outliers, 1035.33. Okay, so the numbers we get here are 721.17 and 2791.83. So we can use that to say we are 99% confident that the mean cost of repair to a mini or micro car involved in a low impact collision is between, and these are in dollar signs, $721.17 and $2,791.83. Okay, did we answer all the questions? I think how far am I over time? Okay, I'm almost 10 minutes over time, so I need to wrap this up for you all. Here we go. Okay, so we constructed and interpreted the 99% confidence interval for the population mean cost repair. Part D, suppose you obtain a simple random sample of size 10, so the same sample size, of a Mini Cooper or Mini Coopers that were in a low impact collision and determine the cost of repair. Do you think that a 99% confidence interval would be wider or more narrow? Explain. So I think it has to do with this idea.
As the confidence increases, doesn't it become wider?
Mm-hmm. Yeah. So more
And
confidence makes the interval wider. So if the interval is wider, so the sample mean, if the sample mean stays the same, let's just say if the sample mean stays the same. If the sample mean stays the same, then the error is what changes. So the more confident that you are, the bigger this number will be, right? Because it'll be wider. So you're adding a bigger number and you're subtracting a bigger number, making it a wider interval. So the more confident, the more wide the interval will be. What affects the error, one is sample size. But in this case, we have the same sample size because we had 10. So they're taking a random sample of 10. And the sample mean might not be the same. I mean, because it's a different sample, of course. But the other thing that affects it is S. And S is the variability, measures variability. So if I think about my cars in my original sample, these are mini and micro. They're mini and micro vehicles. I wrote over it, so you can't see what I wrote, but okay. So right here, it says mini and micro vehicles. So a variety of different kinds of vehicles, mini and micro. So the spread and the variability will be bigger than just Mini Coopers. So if I just took Mini Coopers, the variability is going to be smaller among that particular type of car versus a bunch of cars that are like that. So if that's going to be smaller, then two things will change. The standard deviation will be smaller and the sample mean will also be smaller. So if those are smaller, then my interval will be more narrow and I'll be less confident. So the 99% confidence interval will likely be more narrow because there's less variability in the data since the vehicle variability has been removed. So the variability among the different types of mini and micro cars is now removed and we're only looking at the Mini Coopers. So the variability is going to be smaller, which creates a smaller sample mean and a smaller, definitely a smaller standard deviation. Hopefully that was helpful pulling this together. I know that when you're first learning all of this, especially confidence intervals, that was very new to you, then it might have been a little more confusing at first, but now that you've been in it and you've been practicing it, I just really encourage you to go back to how confidence intervals are created and not rush right into technology. Be really mindful about what you're creating a confidence interval for and use the correct tools for that. Okay, anything that you need from me? You have a test coming up.
tomorrow.
Yes, I do. I have a test tomorrow. So today in 9.3 really was a review of confidence intervals.
Mhm.
So I thought that would be I just don't have enough days to let you spend more time reviewing. So today, hopefully you can review the confidence intervals. It's over chapter 7, chapter 8, and chapter 9, but really all of those have built on each other. So confidence interval has built off of, you wouldn't be able to you wouldn't be able to create confidence interval if you didn't learn about the normal distribution in chapter 7. And then you wouldn't be able to create confidence interval if you didn't understand about the distribution of means. So there are all those pieces that are putting together, and you have one more piece with hypothesis testing that makes it come full circle, and you've learned everything you need to know in a beginning stats class. That part's exciting, huh?
I hope it comes together. I do.
Well, it will.
I know.
So good luck on your test. You don't need luck. Just be prepared so you're confident. That's all you need. Be prepared and be confident. Test corrections are due on Thursday, and there's not a Zoom meeting on Thursday because I'd rather you spend time doing test corrections and learning from your mistakes than listening to me. Okay. I'll see you. Yeah, I'll see you next week. You'll start in confidence interval. You'll start in hypothesis testing on Friday. You'll have your first exposure to that. So I look forward to talking to you again on Tuesday. But keep me posted if you have any questions before that.
Okay, thank you.
Bye.
Bye.